able to see it okay? Let me rearrange things a little bit. Okay. So what I thought I would do is try and review a little bit of what went on in the lab yesterday. So in our last exciting microcontrollers class, we were using the section of the microcontroller known as the ADC converter, and you can see that here highlighted. It's got a couple of external inputs, a ground, an analog reference, and some analog VCC input. And these can all be seen external. Can you see it okay?
Yes.
Okay. So we can see all of these things external. And when you see it external to the dotted line, that represents pins that you can actually access. That is to say, there are connections to the chip from the outside world. We see analog to digital conversion inputs here, ADC 6 and 7, and that's true for some of the quad flat pack versions, not for the parallel dip versions that you find in the Arduino Uno. So we're constrained to port C 0 through 6, which you can see over in here. They're tapped in and going over into the ADC converter. We can also use them as digital I/O ports, should we like to. We set up our data direction register for that, but right now we're just interested in using them as an ADC converter input. And that's sort of the focus of yesterday's lab. We were able to digitize from the ADC converter and then output to our little SPI DAC, and we did that in real time, changed our scaling rates for the sampling, and then proceeded to observe aliasing effects for different frequencies from our oscillator onto our oscilloscope. And that was all very educational and fun. So now let's try and dig a little deeper into the programming aspect of this. And I guess the lesson for today is you gotta read the fine manual, because if you don't, you're going to get really lost in the bit flipping stuff that you have to do to make things work. And what I'd like to do is I'd like to try and relate the programming that you have to do to the hardware that you're having to deal with. And so there's a couple of things going on in this diagram that really don't strike you as particularly obvious. Like here's a little block that says internal band gap and then analog comparator. You know, what's that about, you know? And then you can see the ADC converter feeds into this rather thick looking line. That's your data bus. So it can actually be read to and written to from the data bus. And there's a bunch of registers in here for controlling it. And we're going to examine some of those registers. So let's look deeper into the ADC converter now. And we can see there's a bit of logic going on here. There's this thing called ADMUX, which is the analog to digital converter multiplexer select register, right? And the register contains perhaps 4 bits for multiplexer inputs, but it also has other things, ADLAR, REFS0, REFS1. Now, what's that about? There's this other register here called the ADC control and status register A, and yes, indeed, there is a B, and it has things like ADEN and ADSC and ADFR and ADIF and all these prescaler inputs, which we were playing around with yesterday. And this is stuff that we have to sort of learn about. And then it has these outputs, ADIF, ADIE, and then it goes into some kind of an AND gate that says, aha, my conversion is complete. Let's generate an interrupt request. And that's kind of interesting. So then we look over here and we say, aha, clear ADLAR for 10-bit results. And that's kind of what we're doing here. We say clear bit, and here's in the ADX, clear the ADLAR bit. So there's this 1 bit right in through here. We clear it, and that's going to give us 10-bit results somehow. And in fact, that's taken straight from our code here. Now we know why we're doing it. Let's take a look a little deeper into this ADC multiplexer register. But before we do, we see, oh, here's some more code over here. And it says set bit in the ADC SRA ADEN, which is the analog to digital converter enable. I guess you have to do that in order to be able to use the darn thing, because if you don't enable it, it just doesn't work. So this is kind of an interesting point. This is, how would you know to do that? Well, got to read the directions. So let's dig a little deeper and see how all of this comes together. So here's a blow up of the analog to digital converter multiplexer register. So keep in mind, that's this thing right over in here. It's highlighted with the yellow. And here are the bits, right? For the 4 bits worth of multiplexer, we go bits 0 through 5. So we're only using the least significant 3 bits for selecting the multiplexer input. And keep in mind, there's only one analog to digital converter here. We just have to analog multiplex the input lines and choose which one we want to use when we want to do our conversion, because we can only convert one line at a time, because we only got one ADD converter, and that's it. And then there's this thing here which I snarfed from the data sheet, and it says there are these bits, and the most significant 2 bits of our AD-MUX register, and they say, well, look, if you set it to 0, you use an external analog ref, and the internal ref is turned off. If you set it to 0, 1, you use the VCC with an external capacitor. And then there's a reserve thing, which we don't use at all, 1, 0. And then 1, 1, there's an internal voltage reference. And so what do I do? Here's my code. I set REF 0, so that makes this a 1. And then I clear REF S1, that makes this a 0. So 0, 1, and you can see what I wrote in here. I wrote VCC REFS in binary 0, 1. So 0, 1 means I'm going to do the VCC as my analog reference. And that's convenient because we always have power, but it's inconvenient in another sense, because if the power grid, if the power supply fluctuates just a little from 5.2 down to 4.8, it's going to throw off the whole ADD converter. And if our sensors output analog voltages or current, then it's going to throw off all our sensors too. So inaccuracy in something like a thermocouple will show up with an extraordinarily high variance in temperature. So if you have a need to have precision, this is not a good way to go unless you can be sure that you have a precise VCC. And we're never really that sure of our VCC. In fact, we could run it through a regulator and make, a common measurement, but it's really nice to know that there's this voltage reference here, and we can modify things a little bit if we want to do the voltage reference. So that's kind of neat. Right now, we don't care that much. We just want things to work. And so we're going to do the convenient thing. We're going to set REFS0 and clear REFS1. That gives us a 0, 1 and says, okay, let's use the VCC. So that's where that comes from. And you say, geez, Professor Lyon, this is too much detail. We don't need to know all this detail. Yes, you do. And the reason why is because if you don't do this stuff, it just doesn't work. This is not like a compiler error. It's either going to work or it's not going to work. And when it doesn't work, you won't know why. So having these directions in the code kind of makes sense. It lets you know what you're doing. Trouble is, I can't get these pictures into the code. So putting it together in a PowerPoint actually makes it better in a big way. So here it is, the AD-MUX again, right? We saw REF0 and REFS1. And now we can use our knowledge of digital design 1 and electronics to try and relate our code to what's going on. REFS0 was set to a 1. That's the gate to a little MOSFET, and that's going to let voltage pass through, because a MOSFET is a voltage variable resistor. And so what it's doing is it's letting this little 2-to-1 multiplexer go and assert a line going into the 10-bit DAC. And that is your voltage reference input. And you can see how an analog reference, if left unconnected, will be overridden by whatever comes out of this 2-to-1 multiplexer. And then with a 0 being written into REFS1, we can see the 2-to-1 multiplexer is going to select leg 0, which is AVCC. And now you can relate that back to the code, which says we're going to clear REFS1, that's this leg of the multiplexer, and we're going to set SBI S0, that's this little gate input to the FET, the field effect transistor, and that's what allows us to use 0, 1 with the external capacitor at REF pin. Now, put a nice external capacitor in there, and that's going to keep the voltage up somewhat. That's why they're asking for an external capacitor, because they figure if there's fluctuations in the line, they shouldn't propagate to the DAC. So if we're not using an external capacitor, and we're not, then it turns out we are in the we don't care, it's good enough for us kind of camp. And that's all right if all you want to do is digitize, an analog signal. But now you can see how the bits actually relate to underlying hardware and how they route signals around by setting up this little 0, 1 versus 0, 0 thing. So that's kind of cool, actually. And you can see why 0, 0 might give you the analog reference. That turns off this gate, and it gives you a direct outside reference. You see these square pads? That means you can wire to that. There's like a pin on your Arduino Uno. You can actually connect something to this. And that'll give you, if you have a nice stable analog reference, an input to your 10-bit DAC. And that might be cool, especially if you said to me, well, I know that my input is going to range from -1 to +1 volts. Therefore, I want an analog reference that's consistent with that, and I'm going to let the DAC float and digitize something coming right out of my guitar preamp or something like this. So then you could say, aha, I'm going to set my analog reference the way I want it. And that might be a reasonable thing to do. So that's a nice blow-up diagram of what's going on, and it lets you get a little bit of insight into why you're doing what you're doing, because otherwise it just seems like magic, and it shouldn't seem like magic. It should just be something you can relate to directly from your digital design class. And you kind of can, I think. It's a sort of an interesting idea. Let's look again at some of the code and look at the diagrams. So here's this multiplexer register, ADMUX. And it says here there's an ADLAR bit, just one bit in this multiplexer register. So it's not really about multiplexing so much as it is about control. And so that means it's going to do some sort of right adjusted for 10-bit results or left adjusted for 8-bit results. And then you get your results. These will be the 8-bit register. And if you want the 10 bits, you'll need both these registers, which are read into a variable called ADC. And so what you do, this is what we've been doing, is we want to go and clear the ADLAR to right adjust 10 bits. And so the most significant 2 bits are going to be in an ADCH, and the least significant 8 bits will be in ADCL, and we'll get the whole 10 bits in a variable called ADC. And so what we do in here is we say clear the ADLAR, which means clear this bit, bit 5, and then we're going to get our 10-bit results. That's what we want, the nice high dynamic range results. We can go faster if we only want 8-bit results, but we're going to get 10-bit results. And so that's fine. And that's where that comes from, ADLAR. So if we go back and we take a look, and you say, well, where is this ADLAR? I don't see it. Let's take a look at the next line. It should be in there somewhere, I think. Oops. Sorry about that. ADLAR. I am not seeing that. But it should be part of, oh, there it is. ADLAR goes into the conversion logic. So that's coming right out of the AD multiplexer. So there's bits, I think these are bits 7, 6, 5, 4, 3, 2, 1. I think we're skipping a bit. There's one bit that's not used. Yep, there it is. Bit 4 is reserved for future use, they say. I don't know if they're ever going to use it, but there it is. So that's where ADLAR comes into play. And then there's this other thing, the multiplexers. Well, we're just going to either have it set all zeros, or we're going to put a 1 in for the least significant bit. So if we're in the middle of sampling ADC 1, then what we're going to do is we're going to go and set MUX 0. Otherwise, we're going to clear MUX 0. So if we're alternating between MUX 0 and MUX 1, we alternate between setting and clearing. There's another way to do this. If you said, oh, well, I'm going to have, perhaps 5 or 7 different multiplexer lines, I could clear the least significant 4 bits by ANDing with 4 bits that are 0 in the least significant nibble, and then ANDing with 4 bits that are 1 in the most significant nibble. That's 0x f0. And this comes from your bitwise ANDing. The ampersand is bitwise. And then comes a bitwise inclusive OR. Take the least significant 4 bits from the ADC number that's passed in and put them into the least significant 4 bits here. So now you can see where your sort of Boolean algebra is coming into play. And with 0, it makes it 0, or with the ADC number, and it's going to set the least significant bits. And so that's kind of cool. As long as you want to do something like that, this might be a reasonable line of code. But if you're only alternating between 2 ADD converters in 2 multiplexer settings, this is actually a more efficient way to go by at least a clock cycle or something like this, maybe 2. So then, and to that point, I should mention to you, when you read the data sheet on this, it says if you have a 20 megahertz clock on your Mega 328P, you have 20 MIPS, 20 million instructions per second. When you have a 16 megahertz clock like we do, you have 16 million instructions per second. So our clock rate directly links to our architecture, which is a single instruction, single data, or SysD type architecture. So if you make this chip faster, it's going to go faster. There's not multi-cores. There's nothing fancy going on. In fact, it's an 8-bit toaster controller. So here's another little flag for you called ADate. I had to look this up because I keep forgetting what it stands for. That's the Analog to Digital Converter Auto Trigger Enable, ATE. I mean, this is like worse than NASA. Right, NASA has like SRB for solid rocket boosters. Here's ATE for Auto Trigger Enable. And so the A date has to be set. You say, well, why is that? And you can say, well, because look at this AND gate. If A date is set, then the one leg of the AND gate is now enabled. And here's a little bit of code that says SBI A date, and that's going to set the A date for that leg of the AND gate. Just pretty cool. So now you've got automatic triggering enabled. That's nice. That's going to start the count from 0 on the prescaler in order to make everything consistent. And then it's going to detect a rising edge coming out of this analog multiplexer here. And this is the ADTS. Oh my God, what are these guys thinking? And so the DTS is a trigger select. That's the analog to digital converter trigger select. And if you do something like set it to 0, set the 3 bits, the 3 least significant bits in the register to 0, then it's going to take this multiplexer and get the first input, which is called, wait for it, ADIF. I was like, oh man. And here's another one to know. That's the ADC interrupt flag. So when this thing is done converting, it's going to create a rising edge on the interrupt flag. It's going to get ANDed with the auto trigger enable bit, and then that's going to start your conversion, which is cool. There's another thing here called ADSC, which is ORed with all of that, and you can start the conversion manually just by asserting the ADSC for start conversion line, and that'll get your conversion to start as well. So over in here where I said, look, ADC SRB, that's the analog to digital converter, I think it's called status register, is set equal to 0. So the least significant bits include ADTS 0 through 2. That gives us the ADIF input, which is the interrupt flag, so that when this thing is done doing its conversion, we should be able to get the conversion logic provided A date, which I've set, is set to true, and then we'll get conversion logic to start converting for us. So that's where we get some of that code there. It's not obvious. right? I mean, you look at the diagram, it becomes a little bit more clear, but you really have to think about this stuff. And so here comes the ADC SRB. Status register B. That's it, status register. I always forget. So there's a status register A and a status register B for the ADC. And here are the data selects, and you can choose any one 0 through 3. And then there's this little chart in here which says, look, you can make it free running mode. That's what mode, which I set to 0. So that's where you get is free running. You can use an analog comparator, which is really good if you're trying to like build an oscilloscope out of your Arduino, because the analog comparator can check something on like the rising edge of something or other and then trigger. So this could be like a variable trigger input, which you use on your little oscilloscope. And you could have the Arduino act as an oscilloscope. You could somehow devise external interrupts that are going to do conversions, or this is very common, you can use counters. The first counter 0, is like an 8-bit counter, and the next counter 1, is a 16-bit counter, so one's a higher precision than the other. And so you could use counters to trigger the conversion for the analog to digital converter. But we're doing free running mode right now, and that works fine, because when the converter's done, we're going to go right in and start to take that data and output it to our DAC. So we're going to let it run as fast as it can. And if we change our prescaler in order to change the conversion speed, that's going to change the overall throughput of our system. And we've seen how that impacts the quality of the output that we get. It's a big deal. In fact, the way you hear it is a big deal. So and also what it looks like is a big deal. So it's sort of an important quality control factor. And so that's my basic coverage of the code. Now, when you look at the code, it becomes way more clear what's going on, right? Because now when you say, if we're sampling ADC1, we're going to set mux bit 1 to ensure that we're sampling ADC1. Otherwise, we're going to sample ADC0, and we do a clear on mux bit 0. So that's cool, right? And it shows you exactly how we get to where we're getting. Here's the A date, and here's the trigger select bits, TS, ADTS, analog digital converter trigger select. And so we can see why these things are set or how they're set. And in fact, if we go to the head of our code, we can see the ADC SRB is being set to 0 because we want the auto trigger select to be ADIF to show when we're finished with the conversion. So that's kind of cool. Here's the ref 1 and 0, and you can see where we put in a 0, 1 for REFS 1 and REFS 0. That sets our reference voltage to VCC. Here's our bit 5, ADLAR, and what that's doing is it's going to clear the ADLAR bit in order to give us a 10-bit result from our ADD converter. That means we'll be able to grab a variable called ADC every time we're interrupted. We go over in here, and we can see we've got to enable the ADD converter. So we go to the control register, and then we enable ADD converter input. Otherwise, we can't do anything. And then we take a look at this prescaler. And someone said to me in the class, he said, oh, but look, it runs faster if we give it like, I don't know, a 2 megahertz clock for the ADD converter. And I'm like, yeah, sure, it runs faster, but if you read the directions, what it says is frequencies up to 1 megahertz do not reduce the ADC resolution significantly, but operating the ADC with frequencies greater than 1 megahertz is not characterized. I can't tell you how many YouTube videos I saw where people were using 2 megahertz inputs into their ADD converters without mentioning the fact that they have no idea what the resolution is. I mean, it's supposed to be 10 bits. As far as I know, it could be down to 9 bits, 8 bits, 6 bits, Take your pick. Who knows? And not characterized means they don't really care what you do if you want to do that. It's not going to blow anything up, but don't expect it to give you a full 10 bits worth of accuracy. So this is a kind of an interesting point. People kind of ignore the data sheets on this, and it's a little bit maddening. I'm like, why wouldn't they read that? And maybe because they don't read the data sheets, huh? So then it says for optimum performance, ADC clock should not exceed 200 kilohertz. You know, and I'm thinking to myself, 200 kilohertz, that's like nothing. That means I'm going to be down in the, I don't know, 9.6 kilohertz sample rate, because that's 125 kilohertz. Next one up is 250 kilohertz. So that doesn't really float my boat, because if I'm sampling at 9.6 kilohertz across two different ADD converters, I'm really down to a total sample rate for each converter of perhaps 4.8 kilohertz. And that means my maximum clock frequency, my maximum input frequency, according to Nyquist, is going to be half of that, which would be 2.4 kilohertz. And I really want audio to go up above 2.4 kilohertz. So if you're trying to sample from more than one ADD converter and you're splitting the operating rates in this way, you really can't settle for 200 kilohertz. I don't feel it's going to, you don't get good results. I've heard it. It sounds terrible. So, you know, going to a megahertz, that's fine. If you go to a megahertz, then you got 76.8. If you want to split it in two, you'll have 35 kilohertz. That gives you Nyquist, which will probably bring you up to about 16K, which is fine. 16K sample rates, 16K of fundamental frequency into a 35K sample rate. That's fine. So here I am doing a divide by 16. And so I'm dividing the system clock by 16. And so what that means to me is I'm going to have a conversion clock for the ADD converter of perhaps 1 megahertz, which is exactly the kind of thing I'm looking for, because that means I've got my 76.8 kilohertz divided amongst the two ADD converters. So that's actually pretty good for me. And it shows you the trade-off, right? Because if you wanted to go to, let's say, 4 ADD converters, you'd have to take that 76 kilohertz and divide it by 4, because they'd each get the same rate of sampling. So that's a trade-off. Here's the interrupt enable. That's part of that input to the AND gate that enables interrupts to occur. And then we have this other thing, which is, I forget what it's called now. Oh, the trigger enable. And then I do my sample ADC is true, sample 1 is true. That's my flag that does alternation. And then I go through my start conversion. And at the end of start conversion, where we select the 80 mux, we assert the ADSC, or start conversion line, and that lets us begin our next conversion. So that's cool. And then you get interrupts, and they take an ADC vector on input. And now if we're sampling ADC1, we grab the ADC1 and we want to start conversion on 0. And when we write it out, we know we've got a 10-bit ADD conversion, but we've got a 12-bit DAC. So I take the 10 bits and I shift it over 2 bits, because I want to use the full 12 bits when I write out to the DAC and get the full volume. And then if I'm grabbing ADC 0, I just grab that and put it into a variable which I can use for processing later, such as modifying the volume if I like. And then I go through and start conversion on the next leg. Next time this thing's going to start, it'll be after I do the ADSC assertion. And now I'm alternating between sampling ADC1 and sampling ADC0. So there's my little flag, and that's the bang sample ADC1. And that's the code. Now, having said all of that, I know it's a lot, but this is the kind of thing you have to go through in order to run the ADD converter. Having said that, I've made this program much longer because I've added, globs of words from the data sheet so that you could see what's going on. Because going back and forth to the data sheet is a bit of a pain. And not to put too fine a point on it, let me just show you what's going on. Here is the actual data sheet that I've been using to guide me through the lecture. And so what you can do here is you can see, this is the analog comparator control register. We didn't get there. But here's the ADC SRB, analog to digital converter control and status register B. And here is the ADTS lines, which are going to do the selector for the input. And so that's where you get that stuff. If you really want to learn how to use a chip and learn how to program it properly, you got to read the data sheet. And here's some interesting stuff about, this is detail about the band gap reference that they have. And these little guys in here are analog switches that lets you take a band gap reference and use that relative to an analog input and do a comparator. And there's all kinds of interesting stuff we can do to talk about analog comparators and how that can be used to trigger our ADD converter input. So that's the data sheet. It's, there for you to read. It's a lot, really. I mean, this whole data sheet is 662 pages long, and that's for one chip, right? So that's, how can I say it? That's a lot. I don't know how else to say it. If you wanted to, you could find stuff in here, like you could look up ADMux, and you could probably find that in several places. Here's the ADMux in the ADD converter diagram. So that's a pretty cool way to look at it. I think when you look at hardware and relate it directly to the software, you're in an area which is neither hardware nor software, but it's in between the two. And this is kind of where you would find like real product development. You want to write a driver for a new chip, this is the way to do it. You want to build a new device for a biomedical application, this is the way to do it. You don't just have these things fall out of the sky. You've got to like read the data sheets and figure out how to get things to work. And that's the secret to unlocking value for these sorts of devices. And so how many pages does it take to describe an ADD converter inside of a microcontroller? Well, that's a good question. This page is page 246, and it keeps going and going and going. And voltage references, 246. And he's got temperature compensations, comparators, and all these other interesting things. Let's keep going. 246, he's not done yet. Yeah, now he's done. So 261. So a little less than 20 pages, perhaps 15 pages to read, but it's dense. And that's the upshot of all of that. So are there any questions about the ADD conversion process? I just thought that was a nice way to go here for ADD conversion. I hope you liked my little presentation there, and I hope you found yesterday's lab educational.